Hi, welcome back to part 3 of 4.3, and we're going to finish it off with velocities. So part 1, we talked about these two formulas. We have circumference and area converted to arc length and still sector area. Part 2, we applied it. We did some two big problems with it. And now in part 3, we're going to now talk about a bit more. So you have arc length, you have area. But then what is this often used for? And now when we talk about distance, when we talk about a length of something, a couple things that we do use it for, yes, we use it for area, we use it for some geometry stuff. But also, especially if you're in physics, we talk about when there's distance, we often talk about time as well. So how fast something is changing. And this is due to, like, in real life, there's a lot of motion. And motion is really hard to capture, and calculating it uses math quite a bit. So one thing we could do is, let's say I have a door. I'll draw a door just first. I have a door. And it swings open and it swings closed along a little hinge. So a little top-down view, what it looks like is I have a door right here. It swings open, it swings closed. This is actually a circle where the center is at the hinge and the doorknob moves in a circle. A wall might stop it, but if the wall wasn't there, it would still move all the way around and loop all the way back. We could see circles in a lot of things, and things move in circles quite often because it is very easy to do. And now we want to use a math to find and describe this movement. So we actually have two types of velocities that we want to find. Velocities. The first one is angular velocity. So how big of an angle am I moving per time? And this is given as omega equals theta over time. And we just take whatever angle I'm traversing over how long it takes, and that is my angular velocity. This is often in radians per whatever time you have. So it's it could be radians per second, radians per minute, radians per hour, per millisecond, anything. The other velocity that we have is linear velocity. But the distance that we're traveling is not a straight distance. Like a car would move in a straight distance. Like from here to here. It traveled 2 miles forward. It still might curve a bit, but then you still could track it in a pretty easy fashion. We want to track the distance traveled. And distance the door travels is along a smooth curve. And how do we talk about a curve? The length of a curve? We use arc length. So velocity, instead of being distance over time, it is actually arc length over time. So we have these 4 formulas now. So the first two up here, and now we have omega equals theta over time, and velocity equals arc length over time. And let's practice this with a problem. So this was from our review. We'll do the other one later. So we have Matt spins a Lazy Susan at a restaurant at 2 revolutions per second. So Lazy Susan, for those who might not know, is something that could rotate. The thing, like, you might have seen a cake spinner if you decorated cakes before, or you've seen someone decorate a cake. It's like a little elevated platform that you can spin around and it moves in a circle smoothly. A Lazy Susan is a very big one. So Matt's spinning it at 2 revolutions per second. A couple of things that I want us to find. First, I want to find, the goal of this is to find our velocities. But let's build some guiding questions first. So first off, what we want us to find is how many radians is a salt shaker traveling per minute? Is an object on the Lazy Susan traveling per minute. Because we want to see how fast it's moving. And what we do with movement, you just pick a point and we see how fast is this moving around. And we use minutes for this. Actually, let's not do minutes. Let's actually change it to seconds. So how many radians is the object on a laser traveling per second? Let me see, in 1 second, it's making 2 revolutions. It's spinning twice. And this is a concept, a little concept check, being like, if it makes 2 revolutions per second, how many radians is traveling per second? 1 revolution equals 2 pi radians. So 2 revolutions equals 4 pi radians. So it is traveling 4 pi radians per 1 second. And that little bit that we just said is kind of the part that ties it into velocity. So what is the angular velocity of an object on the Lazy Susan? And the angular velocity of an object will be omega equals theta over time. So we're going to find a theta and a time that do relate to one another. And we see up here, 2 revolutions per second, 4 pi radians per 1 second. So my theta equals 4 pi, and my time equals 1 second. So 4 pi radians per 1 second. My angular velocity is 4 pi radians per second. So we found some angular velocity with this. The hard part of angular velocity is probably this conversion. Given a set amount of revolutions per a time, you must convert this into radians. So we have that. Next up, I now want to find the linear speed in meters per second of a dish that is 0.75 meters from the center. And I'm gonna send this away. But let's draw this on our little diagram. So my little Lazy Susan, little object that is 0.75 meters away. And it still spins. And it was a bit messy in mine, but we see that the 0.75 is actually a radius. So let's get the linear speed formula out. Velocity equals s over time. I then replace it to see s equals theta r. So theta times r over time equals my velocity. Theta is 4 pi, r is 0.75 meters, time is 1 second. And this gives me a result of 4 times 0.75. Gives me 3 pi meters per second. And at this point, there's a little trick that we will use quite often in this class. I'm going to bring this formula out. I expanded my linear velocity into this form, which will happen quite a bit. Because it's very rare that we do know the arc length immediately. My velocity is theta times r over time. Looking back at my other formulas, I see my angular velocity is theta over time. They're both very closely related. I see I have my theta over time right here. if this is theta over time, let me just rewrite my velocity formula as theta over time times r. This is true. So now I have velocity equals omega times r. And this is another way of writing the formula. You could plug it in, and we'll actually plug it in right here. My omega is right here, 4 pi radians per second. Velocity is 4 pi radians per second times 0.75 meters to get 3 pi meters per second, which is the same answer I had before. You can use the formula in my class. You could memorize it, you could use it, but I will not give this to you. I'll only give you velocity is arc length over time. It is up to you to make this connection. Either the connection that we did the first way, or the connection that this could be replaced to get omega times r. And now the last little example that we'll do together is the linear speed of a teacup on a lazy Susan is this. 0.25 pi meters per second. How far away from the center is this teacup? Linear speed equals theta r over time. Oh, actually, I jumped the gun. Arc length over time. So my velocity equals theta r over time. We have my velocity as 1/4 pi equals 4 pi over 1 second times r. I now divide. So pi over 4, dividing it by 4 pi, divide by 4 pi. That was very messy, but let me just clean it up. I'm actually just clean it up first. Pi over 4 equals 4 pi r. Divide by 4 pi now. Pi over 4 divide by 4 pi. So it's multiplied by 1 over 4 pi equals r. The pi's cancel out. So 1 over 16 equals r. 1 over 16 meters. Once again, we're just being flexible with these problems, with these formulas. So please continue to practice. Actually, let me just keep this here. If you want to practice, read this problem in class before. Also, like what we talked about before, please look up angular velocity and linear velocity problems. You also add in, like right here, angular velocity and linear velocity practice PDF. And one other thing to add, if you feel like your questions that you're getting are not really up to our level, was too low or too high, type in PreCalculus. PreCalculus is probably the most, not really controversial, like most broad class, because PreCalculus is not really set in stone. Calculus is kind of set in stone because there's a standardized test for it. Algebra 1, geometry, those are kind of set, but PreCalculus is kind of very school to school. But this will help narrow your search. Good luck. Please email me if you have any questions.